Welcome to the online causal inference seminar. Today we have Dean Eckles from MIT speak about noise-induced randomization in regression discontinuity designs. This is joint work with Nikolaos, Stefan, and Han. All of them are with us today and are happy to answer questions in Q&A. So please, if you have questions, submit them there. Dean will also stop from time to time to take questions from the audience. All right, after the talk, we will have Michal, Kolesár from Princeton have a short discussion. And then afterwards, if we have some time, we will also take some more questions from the audience. All right, that's it from my side. I'm now switching over to Guillaume, who will handle questions from the audience.
Thanks, Dominic. So as Dominic mentioned, we are very, very lucky to have Stefan, Han, and Nikolaos who will be manning the Q&A. So please do submit your questions there. We will select a few questions to ask to Dean when he pauses. So if your question is selected, we will reach out to you and unmute you. So and I'll ask you to raise your hand. So please do not raise your hand until I've asked you to do so. That's basically it. I think you know the drill now. So it's Dean, whenever you're ready.
Okay. So it's really a pleasure to be able to present in this seminar series alongside a lot of other really excellent work in causal inference. And so what I'm going to talk about today is an approach to regression discontinuity designs that I think helps really connect them with the kind of design-based thinking that many of us in causal inference are concerned with. And so this is joint work with Nico, Stefan, and Han. And I think you'll see their individual fingerprints all over various aspects of this work. So it's really been a pleasure working together on this. So the regression discontinuity design was introduced by Thistlethwaite and Campbell in 1960, where they examined what the effect of becoming a national merit winner was on various downstream educational outcomes. Here, we're looking at a plot of the aptitude test that's used to qualify for being a national merit winner. So on the right side of that discontinuity, these are the people who qualified to be winners, whereas on the left side of that vertical line, these are the people who did not qualify. And then the outcome here is the percent of students who go on to win scholarships, right? So the idea was that by looking at a discontinuity right around this threshold where people qualify or do not qualify to be this national merit winner, we could examine the causal effect of getting this this endorsement, this winning this national merit scholarship. And so the idea is that this could have a lot of advantages over other observational causal inference methods, because unlike other methods, we know exactly how people are assigned to treatment. If their score is high enough, then they're treated, whereas if it's not quite high enough, they're not treated. Actually, there was kind of a long quiet period in terms of regression discontinuity designs, but around 20 years ago, there was really a new boom of both applied work and theory on regression discontinuity designs. And using test scores has been a common case of this running variable that determines assignment to treatment. So here's another example, very similar actually to this classic Thistlethwaite and Campbell example where students are taking the PSAT test and either qualifying for this National Hispanic Recognition Program or not. And we can see how just barely qualifying seems to be associated with being able to then go on to attend different four-year institutions. Test scores make up a lot of these kinds of examples. Here's another example of looking at whether you go on to the next grade after 8th grade or are retained based on test scores. How does this end up affecting whether someone is convicted for juvenile crime? So some of this additional attention during summer might actually reduce whether people are convicted of juvenile crime. So the regression discontinuity design has been used in all kinds of public policy and economics applications. And a lot of people find it to be one of the most credible non-experimental designs. It's also used a lot with medical tests or assays. And so here's an example where that we'll return to, where Bohr et al. Look at eligibility for antiretroviral therapy for HIV/AIDS patients. And that eligibility during this period in South Africa was determined by the individual's measured CD4 count. And so if they had a low enough CD4 count, they'd be put on antiretroviral therapy immediately. Whereas if that CD4 count was a little bit higher, that might be deferred until later. And here we see that there's kind of this, this jump right at this 350 CD4 count threshold. And on one side, these patients are retained, keep returning to this clinic more frequently, right? So this isn't maybe the outcome that we care most about, which might be mortality, but it is allowing these patients to be retained and come back to the clinic. So these designs have become quite common. So let's think about what the standard regression discontinuity design setup is. The idea is that units are assigned to some treatment that will denote with W. If an observed running variable ZI exceeds some cutoff C. And there could be more complex versions of this, but we're going to think about just a single running variable exceeding some cutoff. And then that thereby reveals one potential outcome, the potential outcome determined by whether they're on one side of this cutoff or the other. Okay. And so throughout, we're going to assume that we have this IID samples of this kind, where we have IID samples of this running variable and the outcome, and that typically we also know where that cutoff is. So when thinking about these regression discontinuity designs, especially in the context of the examples I've just shown you, where we're working with educational test scores or medical assays, it's really common to appeal to the idea that there's some perhaps random factors that are outside of the control of individuals, perhaps who are trying to optimize outcomes for themselves, that determine the running variable, right? So though I'm maybe trying to do well on the test, I don't have perfect control over my test score. I can't just decide, well, I want to get exactly 99% on the test. And so in this example from Bohr et al. Mentions that there's just these measures that determine treatment eligibility. These running variables are subject to random variability due to measurement error, sampling variability, and chance factors that could affect, biomarkers as well as performance on educational tests. So this motivates the idea that then people right around this threshold are as if randomized. Their characteristics that are unobserved, these confounders that might bias our comparison as an estimate of treatment effects, are balanced right around the cutoff, just as we would have in an RCT. So sometimes people explicitly argue that units are randomized to treatment in some neighborhood around the cutoff, that units are effectively randomly assigned to treatment around that cutoff. But it's often ambiguous, how large really is this neighborhood? Is it actually a finite neighborhood, or is it only infinitesimal? Are they actually being assigned to treatments with equal probability? So here, returning to this example with CD4 counts, Bohr et al. Write that because there's random measurement error in these CD4 counts, right? People's blood is just being sampled. We don't take all of their blood, right? That whether they get this immediate treatment, whether they qualify for immediate ART, or whether they get deferred ART, is effectively random for people who have CD4 counts right near this threshold. And there's this appeal to measurement error, right? But I think it's a little unclear, okay, exactly how large is this area around this threshold? And can we more directly make use of measurement error in understanding the foundations of a regression discontinuity design and actually use that in estimation and inference? That's what we're going to do here, is use some quantities that are known, describing the measurement error in the running variable as the foundation for identification, estimation, and inference in regression discontinuity designs. And we think this puts these designs on a more design-based footing in some ways that I'll articulate in a second. One just interesting historical note is that Thistlethwaite and Campbell, you might think, discuss measurement error, given that they're studying in art and RD with test scores. But actually, they really don't discuss it at all. They just, the only time they discuss measurement error is to say, well, measurement error is often a big problem in matching strategies or other adjustment strategies where you're only matching or adjusting for noisy measures of the confounder. So I think this perspective, though it appears in the literature, appears a little bit later, kind of in the second wave of RD rather than in this initial introduction by Thistlethwaite and Campbell. So certainly I think this idea that appeals to measurement error and randomness in the running variable motivate the regression discontinuity design, that's in the literature. Our goal here is to really formalize this, to connect this with the actual process of identification, estimation, and inference. So the rest of the talk is going to look like this. I'm going to talk a little bit more about existing approaches to regression discontinuity designs. Then we'll present our approach. I'm going to consider an application, this one that I already mentioned, of CD4 counts determining access to antiretroviral therapy. We'll then do some more kind of simulation studies to evaluate this method and compare it with some other methods, and I'll conclude. So a lot of existing approaches to analyzing regression discontinuity designs actually are based on the idea that there's a continuous mean function for the outcome. And so what's identified under this kind of a setup is a treatment effect that's defined by limits taken from either side of the discontinuity. So we take a limit going towards this discontinuity from above and below, and that's the estimand that's identified here. So a couple of things about this estimand. One is that it describes an infinitesimal population, right? So this is an average treatment effect for no one. It's not obvious that this was of interest ex ante, though perhaps it is quite relevant to small policy changes, right? This does tell me if I were to slightly change this threshold, what are the effects? So that's just a comment about kind of the estimand. There's been a lot of development in terms of identification, estimation, and inference with these methods. And so increasingly there's recognition that naive estimation of this quantity just using local regression on either side of the discontinuity results in some bias, which can be accounted for in inference using some of the methods we'll compare with. And then increasingly, there's also approaches that move beyond just trying to estimate this via regression from both sides and try to directly exploit assumptions about smoothness of the outcome function in order to construct some weights that are in some sense optimal for estimating this regression discontinuity parameter. I think there are some kind of challenges with this continuity-based approach. One of the ones that's, I guess, most conspicuous is that discrete running variables are ubiquitous, right? Maybe you get a particular number of items on the test correct. Even in a medical assay, there's some amount of blood that's getting sampled. So effectively, this number may actually be discrete, you know, even if it's, you know, many, many valued. Some of that's been addressed by Michal and colleagues, though I think this requires a lot of machinations in order to be able to, you know, shoehorn a discrete running variable into a framework that's described by limits from either side of this continuity. I think what we particularly notice is that really this continuity-based approach doesn't meet the criteria for design-based inference outlined by Rubin and others, whereby we should think about our estimation and inference as justified by randomness in the treatment assignment alone, right? That somehow we don't need to peek at the outcome. We don't need to model the outcome in order to decide how we're going to do estimation. So in some sense, these continuity-based approaches are the most theoretically sophisticated, and the estimation, I think, is the most sophisticated. But there's this kind of disconnect between this and the intuitive ideas behind regression discontinuity, where we think of people getting as if randomized on either side of the discontinuity. On the other hand, another approach to RD designs is the local randomization or randomization inference approach. And so this takes literally maybe the idea that units near the cutoff are randomized to treatment, or at least they're as if randomized. So the idea is that we just posit that there is some non-trivial, non-infinitesimal interval around the cutoff, such that within that interval, we have unconditional ignorability, that is unconfoundedness. And so it's as if units are being randomly assigned to treatments. Now, while design-based, this assumption is really typically implausible given the characteristics of RD designs, right? We usually expect that the running variable is something that is quite prognostic for the outcome, right? That's often why it's being used in order to determine treatment, right? People are being given scholarships based on their test scores precisely because the scholarship is designed to recognize people with high test scores, for example. People are being retained in grades precisely because the idea is retention would be helpful for those people who are not scoring on tests at their grade level. Okay. So I think that just taken literally, this ends up being implausible. There are some kind of recent extensions here that try to address this in some way. So Branson and Michal allow for units in this interval to have potentially heterogeneous probabilities of treatment. But these probabilities need to be just a function of observables, not unobservables. Sales and Hansen assume this kind of ignorability after detraining outcomes. But of course, this drops the nice characteristic that this local randomization approach has, that it's design-based. Okay. So we see this as kind of a tension between a lot of the intuitions about how regression discontinuity designs make sense and actually the statistical theory. So what are we going to do instead? In particular, we're going to impose these two assumptions. The idea is that treatment is assigned based on a noisy measure of some latent variable. This yields then noise-induced randomization of treatment. Depending on the particular draw of noise I get in my running variable, I might be assigned to treatment, I might be assigned to control. I might either pass this threshold or not. So in particular, we assume that there's this noisy running variable. And you can think of as a kind of canonical case of this is that conditional on the latent variable ui, the distribution of the running variable zi is Gaussian with some known standard deviation. Furthermore, we're going to assume that this noise is exogenous. So conditional on this latent variable ui that we have this noisy measure of, the exact value of that noisy measure is independent of the potential outcomes, what people would do if they are assigned to treatment or what they would do if they are assigned to control. So this does involve applying some additional knowledge that we have about the situation to the problem, but we think that this is often going to be quite plausible and that there are a number of settings, as we'll see, where there's rich information available about measurement error in the running variable. Whether this is psychometric information about test scores that have been examined through estimating split half reliability, retest reliability, or through an item response theory model, or in the context of biomedical tests and assays, there's often a lot of rich information about how that assay works. And then in some cases, we may also have other sorts of independence assumptions we can bring to bear if the running variable is, say, a binomial proportion. Okay. One of the things that's going to be nice about imposing these assumptions here is that we're potentially going to be able to identify some additional quantities of interest besides this limit, this standard regression discontinuity parameter. But I just want to pause here to see if there's any questions.
So maybe one quick clarifying question. Are we to understand assumption 2 kind of as a conceptual device that can be applied even if there is no measurement error, or is it really, do we take this measurement error thing very seriously? So this should be applied only when we know that there's measurement error with the conditional density that we actually know, or for which we have kind of rich information.
Yes, but we need to take this quite literally. So we're going to be thinking about cases where really there is knowledge about the the psychometric or biometric properties of the running variable, and we're going to use that information. I think there's going to, as we'll discuss at the end, I think there's going to be a bunch of settings, a bunch of standard RDD setups where maybe this doesn't apply. So this may not apply to all RD designs.
Okay, yeah, that makes sense. I think that's it. We don't have any other questions for the moment. Thanks.
Cool. So what are some of the quantities of interest we might try to study here? So one is what I already mentioned, this kind of standard regression discontinuity parameter. That's this infinitesimal local average treatment effect where we take limits from both sides. We could also estimate a constant treatment effect. So if we just assume that there is some common tau to all units, we could estimate that. That achieves relevance just sort of by assumption. One of the things we're going to be really interested in is the idea that we could actually estimate treatment effects for non-infinitesimal subgroups. So one way of thinking about this is that we could be interested in realistic policy comparisons. So what's the treatment effect for units that would be treated under some new policy pi, but would not have been treated under the status quo? Say we increase the cutoff from C to C prime. What's the treatment effect for those people who have a running variable between C and C prime? Of course, you could also be decreasing the threshold as well. So that quantity, we're going to think about that as actually being this conditional average treatment effect for this subgroup defined by some interval on the running variable. You can also trivially think about marginalizing over Z, as you could actually think about computing some just marginal contrast between two policies, as is common in the counterfactual policy evaluation literature. So I think that's one of the things that we like, is this idea that we might want to go after these policy comparisons that are not just about these infinitesimal parameters. So I want to highlight that definitely prior work has noticed that measurement error can give you some leverage here, and particularly some leverage to reason about treatment effects away from the threshold. And so in Lee and Lemot, there's this discussion of how, depending on the level of measurement error in the running variable, the gap at the discontinuity might be more or less informative about some larger population. So if the signal to noise ratio of the test is extremely high, someone who scores 90% has effectively a 0 chance of scoring near the threshold. So in that case, the RD gap is really not informative about them, right? That when we're computing this difference right at the discontinuity, that it's not averaging over people like that who are going to score 90%. On the other hand, if the reliability is much lower, then this gap that we observe at the discontinuity might be averaging over a much broader set of types of units. So the one paper that actually tries to exploit the notion of measurement error is this working paper by Rakanen, who considers non-parametric identification of effects away from the cutoff, and does this by positing some latent variable of which the running variable, or actually multiple running variables, are a noisy measure. However, in that setup, estimation remains parametric and using a factor model. So we're going to really try to kind of drive through from the start of positing this measurement error all the way through estimation and inference based on that knowledge of that measurement error. Okay, so what are the kinds of estimators we're going to use? I think this will be informative for kind of conceptualizing what we're going to be doing, and then thinking about identification and inference. And so we're going to be working with estimators of this form that are linear estimators where we're weighting observations yi according to some weighting functions, gamma plus and gamma minus. So gamma plus is going to weight only observations on the positive side of the threshold, the treated side, and gamma minus is going to weight only observations on the control side below the threshold. So mu hat plus and mu hat minus are weighted averages of treatment and control outcomes, and we're going to have that the expectation of these weights is 1. So the idea now, obviously, this just gives a very general set of estimators here. So a lot of the magic, right, pretty much all of it has to be in how we choose these weights. So we're going to choose these weighting functions using knowledge of the measurement error and what quantities we're actually trying to target. So what weights we're going to choose here are going to depend on whether, say, we're targeting the regression discontinuity parameter, a constant treatment effect, or one of these policy comparisons you could think of as a conditional average treatment effect for some finite group, finite region of the running variable. Okay, so these are the kind of estimators that we're going to work with. So just to sort of review some of the notation that I've introduced so far and that we'll be using shortly, we have these potential outcomes and then the observed outcome. We have our latent variable UI. Then we observe ZI, which is a noisy measure of UI with some known conditional distribution. We then observe an assigned treatment WI if ZI crosses some threshold. We're then going to have a few functions that we're going to use throughout. So alpha is going to be the mean potential outcome for the potential outcomes under treatment and control as a function of the latent variable U. Tau as a function of U is going to be the mean treatment effect conditional on U. And we're going to have big F and little f are going to be the marginal distribution function in PDF of the observed running variable. We're also going to have these weighting functions that I just introduced, gamma plus and gamma minus. Now, what's interesting about these weighting functions in this setup is that they're going to imply some weighting functions with respect to the latent variable. These are weighting functions with respect to the observed running variable, but they imply, along with knowledge about this conditional distribution, weighting functions with respect to the latent variable, right? And it's that latent variable that we need to balance between the treatment and control sides of our contrast in order to eliminate confounding bias. Okay, so let's dig into that. So how exactly is this noise going to identify our causal effects? So here let's think about how the key ingredient to our estimator, which is this weighted outcome, where the weights depend on the noisy running variable, the expectation of that as a function of the latent variable. We can decompose that into this first term, which is this, what we're going to call these alphas. In this case, this is alpha 1, because it's the case for treatment. And then how much are we weighting the mean outcomes as a function of the latent variable? Well, that's where we get these H's, the implied weights over the latent variable. These are implied by the weighting function gamma that we've selected. Okay, so we have the same thing also for the control case. So if we then do this unconditionally, marginalizing out over the latent variable and rearranging, we get this expression where we have the expectation of this the estimator that we've been considering, or a sort of non-ratio version of that estimator. And we see that it's made up of two components. One is this weighted treatment effect. So where we're weighting the taus that are a function of this latent variable with this implied weighting function for treatment, H+. And then we have this other term that's the confounding bias. This captures the degree to which we haven't successfully balanced the latent variable between treatment and control given these weights. Okay, so as you can imagine, we're going to want to drive down that confounding bias. So from the last slide, this is this expression that we have. We have this weighted treatment effect. Exactly what kind of weighted treatment effect we want to target is going to depend on our estimand. Are we estimating constant treatment effects, the standard regression discontinuity parameter, or this kind of policy contrast? And then we have this confounding bias. If we have some constant such that the outcome function is bounded from above, then that implies some bound on this kind of bias. So if we want to estimate this standard regression discontinuity parameter. That is, that we're going to estimate some tau at a particular value of z. Then we may need to also make some additional assumptions about the treatment effects. We just want to estimate the constant treatment effect, then we only need to put a bound on this, this outcome function. If we're going to allow for heterogeneous treatment effects as a function of the running variable, then we also need to impose some kind of a bound on the treatment effect, the magnitude of the treatment effects as well. Okay, so I think this is a little abstract because we haven't really said at all how we're going to go about choosing these gammas in order to get some of these desirable properties to drive down this confounding bias. But you can kind of see that there's an ingredient here in that we have some bounds on how large this bias could be. And so we can then try to optimize these weights in order to balance this bias variance trade-off where instead of the actual bias, we have some worst case bias. So how we're going to choose the weighting functions is very much inspired by some of the prior work by Stefan and Guido Imbens, where you're trying to optimize these weights. But here we have a bunch of additional information to bring to bear. Okay, and so what we're going to try to do is actually control this bias variance trade-off. And so we're going to choose the gamma plus and the gamma minus in order to minimize this expression that is the first term captures the variance, and then this t squared is a bound on the worst case bias. So then we can control how much we want to trade off bias and variance. But as we try to find the gammas that minimize this expression, we're going to be trading off variance and worst case bias. Okay. So we need to proxy for the variance based on an estimate of the density of the running variable. That's this f bar. So we've estimated that potentially from the same sample or from another sample. So we're going to do this optimization subject to a few constraints. So constraint 3 here is saying that we actually want these to be these weighting functions such that they have expectation 1. Then we want the weights to not be growing arbitrarily fast. So we can't have the weights get too large right around the cutoff too quickly, right? In order to get our central limit theorem, we're going to need to have weights spread over enough observations. And so the weights can't be growing too fast with n. And then, as is common in work on kernel regression, we want to have these kernels have compact support. And so outside of some range around the cutoff, these weights are going to go to 0. So we're going to directly solve this kind of optimization problem in order to select these weights. Okay, so how are we going to do inference here? Say that we've selected these weights. How do we go about constructing confidence intervals? So given these weights, our estimator takes this form that it's the difference in these two weighted means. So we have, as we've considered before, this upper bound on the worst case bias. And then we also have an estimate of the variance. So we can combine those to build bias-aware confidence intervals. So these are going to be intervals that are going to account both for the sampling variability and the potential bias in our estimates. So this is the same kind of thing that Stefan and Guido Imbens did in their prior paper on optimized regression discontinuity designs, and Michal has also done in some of his work. Then we have some results about the asymptotic coverage of these confidence intervals. And so this has some requirements in order to get this, asymptotic uniform coverage. And so the first one here is that we need to actually estimate this density of the running variable using some data that's independent of what we actually use for the rest of the estimation. I think in practice that may not be super important, but you can also do this using sample splitting. And in a lot of cases, we may have other data about the distribution of the running variable, precisely because we have other data about the measurement error in the running variable. We just have some moment conditions on the outcome that actually there is some variance, and that we have some upper bounded higher moments. And then we're going to need that these weights that we're using, these weighting functions that we're using, kind of are well approximated by something that is in fact a weighting function. That is that they're have this expectation of 1, and they're going to be positive in a lot of areas. Right, so we don't want these weighting functions to end up being negative. Okay, so certainly there's a lot more we could say about some of the theory here. I want to turn to showing some examples and simulations, but happy to take questions at the moment.
Thanks, Dean. Yes, we have one question. So let me unmute Jake. Jake, you should be allowed to speak.
Hi, Dean.
Hi.
Hey, hi, Dean. Thanks so much. This is really great. My question was about the variant, what we should expect from the variance of the estimated treatment effects here. If I have some, if the measurement error, say, is very small from some administrative running variable, I might end up with a confidence interval that's either way wider or way smaller than I would get if I were to, say, permute or calculate the confidence interval from some continuity-based approach. And I was trying to figure out how I would kind of actually talk with, say, a policymaker where I would say, hey, I have 3 confidence intervals. You know, the one using measurement error is quite different from the others. Which should we choose?
Right.
I was wondering,
Yeah, so I think actually that could go either way. And in some sense, it tells you about how much really the foundation of your regression discontinuity design is based on noise-induced randomization, and that really you're doing a design-based analysis versus not. So in some of the examples, we'll see the confidence intervals get narrower from using this information. In other circumstances, you could imagine them getting much wider if there's basically no noise in the running variable. And that should be kind of a warning that instead you're not relying on this as an identifying assumption if you are going to turn to some other continuity-based intervals. You're instead relying on assumptions that are directly about the outcome. Yeah.
Perfect, thank you, great.
So actually that's a great kind of transition into the next example, unless there's another question.
I think it's good. We'll let you finish, and then we might keep.
So yeah, so here we're going to return to this application where if HIV/AIDS patients have CD4 counts below 350, they're going to be immediately given antiretroviral therapy as opposed to with some delay. So we're going to reanalyze this RDD that occurred in South Africa. What we're going to bring to bear on this is some additional data from Venter et al., who have repeated measurements of CD4 counts of HIV patients also in South Africa. And so from that data, we were able to estimate the scale of the measurement error. And so we posit that the measurement error in log CD4 counts is Gaussian with standard deviation 0.26. And so we're going to use that as our basis for analyzing this. We're going to compare our results to using these optimized weights, kind of the approach that's maybe most similar to what we do. This other approach that directly exploits assumptions about smoothness and outcome by Armstrong and Kolesár. And then also maybe a bit more traditional of approach of using local polynomials, but this is also with bias robust inference that accounts for the fact that there's bias because we may be under smoothing the outcome function. Okay, so first we can just compare the weighting function that we get, our noise-induced randomization weighting function, compared with the weights that would be generated by this opt-RDD approach from Inference and Wager. And so we see that really there's a lot more fluctuation of the weights. A lot of the weights continue to be not approximately 0, much farther from the cutoff. So here it actually is a case where there really is substantial measurement error in the running variable, And so to get to your point, Jake, this is a case where our confidence intervals can actually get narrower. And so if we look at the results from this noise-induced randomization method with different bounds on the conditional expectation function for the outcome alpha, we can see that we're often getting tighter confidence intervals than some of these other methods. And this reflects that there is a lot of measurement error here, right? If there was not a lot of measurement error, that might not be true. Yeah.
Dean, sorry to interrupt you. You have around 5 minutes left.
Okay, great. Thanks. Okay, so one of the challenges, obviously, with just reanalyzing an example is that we don't know who's right here, right? So we generated these different confidence intervals, what properties they have. That's kind of a general problem in a lot of causal inference, right? Is that it's difficult to evaluate observational methods. And so RDDs themselves are limited as benchmarks for RDD methods. So maybe we could compare with a randomized experiment. Also, a lot of the educational RDDs involve private data. So we thought it'd be really great to come up with a way of evaluating RD methods for educational testing data that relies on public data and functions as a real benchmark. So we construct a regression discontinuity design from longitudinal educational testing data. So we take data from the early childhood longitudinal study for 13,000 children. One of the things that's amazing about that is that they have multiple years of test scores that are actually on the same scale, and each one comes with a standard error that's computed from an item response model. Okay, so then we can use those standard errors as our estimates of this measurement error. Okay, so what we do is we let year 1 be the running variable. Then year 2 is the outcome under control, and year 3 is the outcome under treatment. So thus, treatment is an additional year of childhood development and education. We observe the ground truth treatment effects for every single unit, and so we can vary the cutoff that actually assigns people to treatment, right? And so we can actually control, which outcomes do we want to reveal, right? So as we change the running variable, we're able to change which outcomes are revealed. So we can then, for setting a particular cutoff of -0.7 on this scale, we can estimate the standard RDD estimand, not only right at that cutoff, but at other potential cutoffs as well. And we can compare our estimate to one derived from smoothing splines fit to all of the potential outcomes. And so here we see that the confidence intervals, as you'd expect, get wider as you get farther away from the cutoff, but we're still covering the truth across this entire region. Similarly, we can also estimate these kinds of policy comparisons where we can contemplate changing the threshold from C to C prime, where the new threshold is given on the x-axis here. So we estimate this conditional average treatment effect for units that have the running variable between C and C prime. And again, we see that our estimates and confidence intervals are covering the truth, that here we can just estimate actually simply as an average of the treatment effects within each of these intervals. So I think actually this is just a really nice thing as somebody who wants to do applied work, is being able to actually validate these methods on real data. But we thought we'd also just briefly illustrate this with simulations with a binomial running variable, because this illustrates that this measurement error does not have to be additive and homoscedastic. In the case of a binomial proportion, it's going to be neither additive nor homoscedastic. And so we do a bunch of simulations with 500 units where the latent variable is this uniform variable, and then the running variable is a binomial draw with 100 coin flips with that probability, and then we have a constant treatment effect. So looking at the results from this, as we vary the size of the constant treatment effect, our 95% confidence intervals for the NIR noise-induced randomization approach always have at least the nominal coverage, as do the other approaches that directly exploit continuity in the outcome. RD robust actually undercovers. And furthermore, this is a case where our knowledge of the measurement error in the outcome is really helping us to be more precise. With of our confidence intervals is much narrower, and our absolute error is much lower. Of course, this could be different if there was much less measurement error. If instead of 100 coin flips, we had 1,000 coin flips, 10,000 coin flips, right? The resulting measurement error would be a lot smaller, and this could totally reverse. So I think since we're short on time, I'll just skip ahead and summarize. So I think regression discontinuity designs are really appealing, and in part based on this kind of qualitative description that they're like locally randomized experiments, where units are as if randomized on either side of the threshold. But the formal analyses haven't really made sense of this or utilized this. So we use noise-induced randomization that's coming from noise in the running variable as the basis for identification, estimation, and inference. As I discussed with Jake earlier, compared with continuity or outcome-based methods, the results might have more or less variance. The confidence intervals might be narrower or wider, reflecting how much the measurement alone justifies the design. And we think it's really nice that this kind of approach can be used to study treatment effects for observable non-infinitesimal populations. I do want to highlight that basically this approach doesn't readily apply to all RDDs. It doesn't really seem like it applies to geographic boundaries, close elections, class size. So, you know, when Thistlethwaite and Campbell introduced RDD, they said, admittedly, the class of situations to which it is applicable is limited. Now, it's turned out it's found tons of use. But we would also say, admittedly, the class of situations to which it is applicable is limited. But perhaps this actually demarcates RDDs that do involve known randomization, and so permit a design-based analysis, from those that do not. And so if this noise-induced randomization approach doesn't readily apply to your RDD, it may be on a different footing than ones where it does apply. So thanks a lot. I'm happy to take questions and looking to hear from Michal as well.
Fantastic. Thank you, Dil, for this great talk. Yeah, as said, we will now switch over to the discussion. We will have Michal present, and after that, Dean can respond. And if we have some more time after that, we will allow for some more questions. Okay, switching over to Michal now.
Okay, thanks so much. This has been it's been a great pleasure to read the paper and think about the issues that it raises. So what I want to do in my discussion is to first give a little bit of a background to RDs that is going to be in part a little bit of a repetition of what Dean said, but I'm going to do it in a way that is going to allow me to more easily compare what they're doing to existing methods. And I'll argue that it's actually not so different from existing methods if you look at it from a particular perspective. And then the other thing I want to do in my discussion is to draw some comparisons with how people have been thinking about inference and instrumental variables designs, because I think there's some close links to what the paper is doing and what has been done in that literature. Okay, so as Dean said, the really nice thing about RD is that it has a very intuitive identifying restriction, which is that units close to the cutoff are comparable. And so this is something that you can explain to non-technical people, like you can explain it to your child or to your grandmother, like just how RD works is that we look at people who just clear the cutoff and people who just don't clear it, and these people should intuitively be comparable. And by making this sort of comparison between these two types of people, we get at a treatment effect for people who are at the cutoff. There have been attempts in the literature to formalize this intuition directly. So people have suggested interpreting RD as a randomized experiment within a fixed finite neighborhood of the cutoff, or they've suggested you taking a fixed number of observations, and then asymptotically, if I'm only taking a fixed number of observations, I should only be looking at an infinitesimal neighborhood around the cutoff. And once I do that, I can analyze the data as if it came from a randomized experiment. Of course, the problem with that is that it's not clear, how big this neighborhood should be or how many people I should be taking. There's Another thing people have suggested has been to interpret the cutoff itself as randomly assigned. So for example, in case of test scores, where exactly the cutoff is going to be determined by some administrative concerns. So maybe for some reason there's a budget cut this year and there's going to be fewer scholarship awarded, and so the cutoff randomly for that reason moves. And so you could try and exploit that as to do inference. But of course, the problem with that is that we only ever observe one cutoff in the data, and so we don't really know what the distribution of the cutoffs is. Now, so for these reasons, the standard approach to inference in RD is a little bit indirect. Instead, it assumes smoothness on the conditional means of the potential outcomes. So the conditional mean, so in Dean's notation, mu of W of Z, so that's the conditional expectation of the potential outcome under treatment or no treatment given the running variable. And if you assume smoothness on this object, this is in turn going to deliver smoothness on the conditional mean of the observed outcome. And you can use that to do inference in two ways. You could either essentially do undersmoothing. So you can say, well, the parameter of interest that I'm going to focus on is going to be this treatment effect at the cutoff. So, so if I generally define a treatment effect for a subset of people whose running variable falls into the set script Z, if I set script Z to just the cutoff, this is the treatment effect for the cutoff. And for people at the cutoff. And what I can do is I could then use these smoothness assumptions to argue that that my estimator is going to have asymptotically a small enough bias if I choose the weights in the right way. So if I promise to change the weights so that the weights are going to be putting negligible weight on people who are not in infinitesimal distance away from the cutoff. So another approach that this paper builds on is this bias-aware inference approach, where we directly take into account the fact that if I use an estimator that places non-zero weights on people who are away from the cutoff, this is going to lead to bias in finite samples. And if we focus on linear estimators, this bias is easy to calculate. So once I make smoothness assumptions on the conditional means, so I'm going to say these conditional means are going to fall into this parameter space F, then it's going to be easy to calculate what the conditional bias of my linear estimator is, because this problem of calculating the worst case bias is just a context optimization problem. And it turns out that in many cases, it actually has a closed form solution. And so then you can, once you know this worst case bias, because the estimator is linear, the variance of the estimator is easy to calculate. And because the estimator is linear, I also know that it's approximately normal by a central limit theorem, as long as these weights are not too crazy, but that's easy to verify. And so, so I can just construct confidence intervals the usual way with just add and subtract 1.96 times the standard error, with the only difference being that instead of adding and subtracting 1.96 times the standard error, I'm using a larger critical value that takes into account this potential bias. So this is all well and good, but it raises the question of, okay, how do I justify these smoothness assumptions, that this assumption that this conditional mean falls into some smooth class of function F? And so the way when you ask people, the way it usually is justified is that they say, well, the assumption amounts to the assumption that the manipulation, if there is any manipulation going on in these designs, it's not perfect. So if people try and manipulate their test score to clear the cutoff in order to qualify for scholarship, for example, by studying hard, they can't exactly ensure that they're going to land above the cutoff. And so David Lee has a nice discussion of this in his 2008 paper, where he says that what we need to justify this smoothness-based approach to inference is to think of to ensure that the score, the running variable, is drawn from a non-degenerate, sufficiently smooth individual specific probability distribution. So once I formalize individual specific by saying that, well, conditional on some variable U, so that's the latent variable in the paper, the score Z is distributed according to some smooth distribution P, then by Bayes' rule, it follows from 2 lines of algebra that even if the conditional mean of the potential outcomes given U is discontinuous, the conditional mean given Z is going to be nice and smooth. And so the idea of the paper is to take this justification seriously and say, well, if that is how people justify these smoothness assumptions in the first place, why don't we instead directly place assumptions on the conditional mean of the potential outcomes given U on this AWU function, and on place assumption on this individual specific probability distribution P. And once we do that, then once I restrict AW and I restrict P, this in turn is going to restrict the conditional means for the observed outcome, and I can use that to calculate or bound the bias of the estimator. And so, so this is another way of saying that while the standard approach or this bias-aware approach to inference places smoothness assumptions directly on the conditional mean of the observed outcome given Z, the method that's proposed in the paper does this indirectly by placing restrictions on P and AW. But you can calculate what sort of restrictions on this parameter space you're going to generate once you restrict what P and AW can be. So what I like about this is that it makes this implicit no perfect manipulation assumption explicit. So if we're justifying smooth assumptions implicitly in this way, why don't we make it explicit? And once I do that, I can allow for example, for a discontinuous conditional mean function AW of, and that's going to be fine. So I'm going to allow that people that function's discontinuous and allow for imperfect manipulation explicitly that way. But that's going to be fine as long as this P function is P conditional mean function is smooth. And secondly, as Dean was saying, I can also do inference on sort of other types of treatment effects, not just treatment effects that take the form of a conditional mean of the difference in the potential outcomes given that Z falls into some set. So typically people take this set script Z to just be the cutoff, but the bias-aware inference approach generalizes directly to taking it to be other things. So if I'm say considering moving the cutoff from 0 to 1, then and I want to know how are the outcomes going to change for people if I do that, then this set script Z is going to be the interval 0, 1. And so, but exactly the same calculations go through as before. So existing approaches don't actually require you to focus on the case where this set script Z is just the cutoff itself. But in their case, they can sort of they don't have to restrict their attention to treatment effects of this form. They could also look at other types of average treatment effects. And so one thing that wasn't exactly clear to me and that it would be nice to see is whether there's other types of policy relevant treatment effects that do not take this form tau subscript Z, where their approach could take advantage of. And then my comment on the method is that once I think about restricting PW as delivering restrictions on the conditional mean of the observed outcome, the question then arises, is it more natural to restrict the conditional mean of the observed outcome or restrict these conditional density P and AW and this conditional mean AW? So that's really the key when I'm applying these designs. As Dean said, in some cases, it's hard to, for example, in the case of elections, it's hard to think of what is this noise-induced randomization. In other cases, it may be easier. So maybe assumptions on P may be easy to think about in some cases, but it still leaves the question of how do I think about restricting the conditional mean of the potential outcome given this latent variable U, because that conditional mean function is a latent object, and it may be tricky to think about. So I think I'm running out of time, but I just want to briefly mention that the same sort of considerations also arise in the literature on IV, where this latent variable U corresponds to the error in the first stage regression. And people have also proposed placing directly restrictions on the conditional mean of the potential outcomes given U as a way of trying to tighten inference on things like the average treatment effect in the case of instrumental variables regression. So that's all I had to say.
Fantastic, thank you, Michal. Dean, do you want to respond?
Thanks a lot for those comments. That was really interesting and on point, and I think also helped address exactly what I skipped over in the slides, which was, okay, so the approach that we've offered does imply continuity, and that's something that has been pointed out at least since Lee 2008. What we find is, at least in some cases, if you just sort of look at the bounds on the continuity of the outcome that are implied by measurement error and kind of then turn the crank on the normal continuity-based approaches, that may end up yielding quite different confidence intervals. They might be much wider if you're just sort of exploiting it through the continuity and the outcome function, as opposed to the specific information about the measurement error. But I think that's definitely a relevant question for study. I think there are cases where, despite this kind of design-based idea, we might want to use past outcomes to impose these smoothness assumptions. So anyway, I really appreciate those comments. It's been a pleasure to share this new work with everyone, and I really want to thank all of my co-authors for also joining and helping to answer some questions and stuff. So thanks.
All right, fantastic. Thank you. 1 second. Yeah, so first, thank you all. Thank you, Dean, for a great presentation. Thank you, Nikolaos, Stefan, and Han for helping us out in Q&A and answering questions there. Thank you, Michal, for the discussion. Yeah, before we stop, 2 more things. So first of all, next Tuesday we have Jonas Peters from the University of Copenhagen. We're very excited about that talk. Also, if you haven't filled out the survey yet, please do so. You find the link in the chat. All right, otherwise that's it from us today. Thank you all for joining, and hope to see you all next time. Thank you.